Howdy, everyone. How are y'all doing today? What y'all think of the exam? How'd it go? Was sort of hard, tough compared to the last one. Yeah. Usually the exams build in difficulty until the final, and I always tell people this. The first few exams are usually relatively easy, but the final is quite a bit tougher than all the midterms. Just the material on the final the calculations are really long. The stuff is a lot harder to understand intuitively what's going on. And it's just everything's a lot more complicated on the final. So just keep that in mind. But cool. Okay. You'll have homework for 14.7 and 14.8. It should be. I think I might have assigned it right after you looked. It should be assigned right now, though. I think I sent out an email saying it was assigned, or maybe I did not. I might not have. But yeah, 14. Yeah, I think I did actually. 14.7 and 14.8 are going to be due. So 14.7 is due on Friday, and 14.8 is due on Saturday. Yeah. I think I put the homework up a couple days ago. Yeah. Should have sent out an email, but so okay, so we have a new course coordinator, and I'm not certain how he's going to do things. So the way it worked I suspect it'll be similar. The way it worked with the previous course coordinator was the individual exams were not curved. What happens was we took into account the averages over all the exams, and use that info to adjust the cutoffs for the grades at the end. So if the grades on a few of the exams were on average quite low, then we'll adjust the cutoffs to where it's easier to get, say, a B- or et cetera. So all the cutoffs will be adjusted down a bit. The problem with that, though, is if you're a student, the process is a bit opaque, right? Like you can't look at your grades here and see how you're doing until kind of the end, and you don't ever actually know what the actual cutoffs were. We're not supposed to tell you guys, because then we get a trillion emails and every single person saying, "Oh, I was this close to the actual cutoff. Could you bump me up, please?" So yeah, in general, we don't curve directly the exams, but we do take the averages into account and then use that in finalizing or deciding what the grade cutoffs are at the end. So there is a curve. It's just not not as clear how it's working for you as a student, unfortunately. Will I be able to tell you what the average was on the test when it's graded? I could, yeah. I could. I plan on grading probably Thursday or Friday. So how many points? It depends. It really depends. Like sometimes there's like a particularly brutal final exam where the grades are just like abysmal. And honestly, I don't remember like exactly how many points either. So usually it's not Usually it's not too many, though. But it's hard to say also because it's a new course coordinator. So I'm not sure exactly what his policies are going to be for this. So I don't want to mislead you either way. So sorry about that. I'm not 100% sure how that's going to work. I suspect it'll work similar to how it worked in the past, but exact numbers, I'm not actually sure. Yeah, that also depends on how the exams go this semester. So yeah, and that is also hard to tell how it's going to go until probably the last two exams, the final and the next exam, because those are where those tend to be tougher and the grades tend to be lower on those. Okay, anyways, right, so let's get started. What will the next exam cover? I mean, it's in the syllabus. The exam covers, let's see. I mean, I kind of got to get rolling, but let me check real quick. Gonna guess it's gonna cover all the integration material. Yeah. Yeah, so it's going to cover up to the end of this chapter, basically, chapter 15, multiple integration. And then we get into the vector fields and then the integration theorems. And that's the stuff that's heavily emphasized on the final. The final is comprehensive, but like probably in the past, like 40% of it has been newer material. But yeah. Okay, so we're going to start covering. Now, we looked at differentiation of functions of multiple variables. Now we're going to look at integration of functions of multiple variables. And so we're going to start with double integrals. In particular, the simplest case of integration of double integrals over rectangles. Okay. So if we have a function of two variables, so here's what this is. So I'm going to draw a really simple surface here. So suppose this is a graph of a function f of xy. So this is a surface z equals f of xy. I drew a really simple one here. Use your imagination to make a more complicated one. But okay, so suppose we have some region in the plane, in the xy plane, D. So region D in the xy plane. We have a function f of xy. We look at the graph of the function of f of xy. So the graph is a surface. And suppose for now that that lies above the xy plane. So suppose f of xy is positive, at least above D. So if we look at the region above D and below the graph of f of xy, whoops. So we're going to get some solid region here. So we have a solid region between D, some region D, in the XY plane. And the graph of f of xy. Oops. The volume of this so the volume below the graph of your function f of xy and above a region D in the xy plane is going to be the double integral over D of the function f of xy with respect to area, dA. So the double integral over D of a function f represents if f is positive, right? If f lies above the xy plane, the graph, the volume of the region between D and the xy plane and below the graph of f is the double integral over D of the function f. So same thing, it's like area below the curve. Now it's volume below the surface. And that's if it's positive. Of course, if it's negative, then it's negative of the volume.
Can you go back for like 2 seconds, please?
Sure. All right. Let me just write that here then. Oops. So we get negative the volume if our region or if our function is negative on D. So it's like, oops, let me do it like this. It's like integrals of functions of one variable where we're positive, we get positive of the area, and where we're negative, we get negative of the area. So you add up the positive parts minus the negative parts. But in this case, it's volume below the surface. Okay, so the thing about double integrals is when you're doing single integrals, we generally learn to integrate over an interval. There are other kinds of integrals, and that's beyond the scope of this class. But single integrals generally we just do over intervals. For double integrals, we do over regions in the plane, and those can get a lot more complicated, right? The simplest regions are what we're going to look at today, and those are when the region we're integrating over is just a rectangle in the plane. So if we look at a rectangle, so we're just going to look at the set of points where x goes from A to B, y goes from C to D. Oops. So that's going to be, suppose this is A, this is B, and this is C, this is D. So that's our region R. X goes from A to B, Y goes from C to D. And we often use shortened notation. We just say the interval AB cross the interval CD. And this means if you look on the x-axis, X goes from A to B. And if you look on the y-axis, Y goes from C to D. These are going to be the types of regions in the XY plane that we're going to be integrating over. Yeah, I'm not even gonna attempt to draw a picture here. Let me. Here's what we're gonna be doing. So we're gonna be, remember we said the double integral over, in this case, the region R, is gonna be the volume of the solid below the graph of our function, the surface z equals f of xy, and above the rectangular region D, or R, in the xy plane. So we're going to estimate this volume. So we're the process for defining these integrals is going to be by approximation. So we're going to split R up into subrectangles, and then we're going to pick a point in each one of those subrectangles, and we're going to assume the function is constant on that rectangle. In other words, the function represents the height of that rectangle. So if we assume it's constant here, if we split up into small enough rectangles, it's approximately constant there. And so we say like the height of this guy's constant. And so we're just looking at the volume of this, each of these little pieces. And these are all going to be just rectangular prisms, right? And so the volume of that is just height times area of the base. Since we're assuming the volume, or sorry, we're assuming that the function representing the height is constant on there. And then we're going to add all those up, and that's going to be approximately the area, the volume below the surface. So as we get smaller and smaller rectangles, we're going to get closer and closer to the actual area, and then in the limit we get the actual area, and then that's going to be how we define the integral. And that's how we're going to do all of our integrals. So let's really quickly go through that process. So what we're going to do is we're going to chop up A to B So in the x direction, we're going to chop up A to B into m equal pieces of length delta x. So we break it up into m pieces in the x direction. Each of these are going to be length delta x. Suppose they're equal here. And then we're going to divide in the y direction. We're going to divide C to D into n pieces. So n equal pieces of length delta y. So pretend these are all equal subrectangles. So we have m times n of these guys, and each of them has area delta x times delta y. So each subrectangle has area, we'll call it delta A, but it's just delta X times delta Y. And we're going to label all these. So this first guy here is going to be rectangle 1, 1. This is going to be 1, 2. This is going to be 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, etc. We're going to call them rectangle R, I, J. So let's pick one of these guys. Let's say this guy right here. So in the ijth rectangle, rectangle Rij, pick some point. Doesn't matter which. Just pick any point in that guy. We'll call that the point Pij. So it'll be, the coordinates will be X, Ij, Y, Ij, but I'm just using Pij to save a bit of time. Okay. So we want to approximate the volume below the surface and above this little subrectangle. So we're going to assume that the function is constant on the entire subrectangle, and the value of the function, the height of our prism here, is just going to be the value of the function at the point we picked. Sorry, the volume above this little guy, above Rij, is approximately the, sorry, let me just say it this way. The volume is approximately, so it's going to be the area of the base, which is delta I, and then we're assuming the function is constant because get a small enough rectangle, it's approximately constant. So the height is going to be the value of the function at our point. It's not going to be exactly the volume below there, but it's going to be approximately volume. So this is the height of our prism. Delta A is the area of the base. So that's approximately the volume below the surface on this one piece. And then we just add up over all the pieces. You do the same process. For each of these pieces, you pick a point. You assume the function's positive. In other words, the height of your guy's positive above each of those points. And each of them has volume, the value of the function at that picked point times the area of the base, which is delta A for all of these. So the volume is approximately equal, the total volume. So you just sum over all these guys. So I equals, whoops, 1 to m. J equals 1 to n. So the FPIJ delta A is just the area, approximate area of each of these guys, and we're summing over all of them, adding them all up. So as you break them up into smaller and smaller pieces, so as m gets larger, you break AB into more pieces, and n gets larger, you're getting a better and better approximation of the volume below there because the point you pick, the value of the function is going to stay closer to that, the smaller and smaller the piece you pick. And so, in fact, in the limit, if your function is nice, then you get exactly the volume, which is the integral. So our definition so if R is the rectangle AB cross CD, the double integral over R of a function f is just do this whole process, but take the limit as m and n go to infinity. So you break x into AB into more and more pieces, take that limit to infinity, and then CD into more and more pieces, take that limit to infinity. So it's just the limit of these double Riemann sums. Okay, so if you remember all the way back to 140, doing Riemann sums was not fun at all, right? It's a giant pain. And then doing limits is also not super fun. Double Riemann sums are going to be twice as awful, and we're not really going to evaluate integrals in that way. We'll see in a second how we actually evaluate integrals, but this is the definition of the integral. Just the limit of these double Riemann sums. So you're approximating the volume and then taking a limit. That's how all of our integrals are going to work. Okay. So a couple things I want to say. These will help in just a second. So double integrals are going to work the same as single integrals in the following aspects. So they're going to be linear, right? So if you have the integral over R, some rectangle R, of f, so one function of two variables plus another function of two variables, you integrate the sum over R, that's equal to the integral over R of the first, plus the integral over R of the second. See, the integral of the sum is the sum of the integrals. And then similarly, you can pull a constant out of the integral. The integral over a rectangle of a constant times a function. You can pull that constant out, and that's a constant times the integral over R of the function. So these two together means the integral is linear, right? Integral of the sum is the sum of the integrals, and you can pull your constant out of the integral. Also, just small point, we'll emphasize this more later. If your function that you're integrating is just the constant function 1, so if you're integrating, yes. So if you're integrating the constant function 1, then this is equal to, remember, it's the constant function 1 is just the plane z equals 1, parallel to the xy plane. So it's a horizontal plane. The volume of that, it has constant height 1. So the volume is just going to be the area of the base times the height, which is 1. And so the volume is just going to be the area of the base. So if you integrate the function 1 over the rectangle R, that's equal to the area of the rectangle R in the xy plane. That's actually very useful and will be used later. Same is true, you can integrate over any weird region D in the xy plane. And if you integrate 1 over D, you're always going to get the area of that region D. Okay. That's a small kind of unconnected point to what we're going to talk about now. But so how do we actually evaluate these integrals? Well, let's look at iterated integrals and see how these relate. Okay, so we have a function of 2 variables. So we can take partial derivatives of that function, right? So the partial derivative of a function with respect to x is you treat y as a constant, and then you differentiate as usual using 141 rules with respect to x. So you can do partial differentiation by treating one of the variables as a constant and differentiating as usual with respect to whatever variable. And you can also undo that by doing partial integration, right? So suppose I have a function of x and y. And suppose I just integrate this with respect to y. Say from y goes from C to D. So this is the opposite of partial differentiation with respect to y. So we're going to treat everything but y. So we're going to treat x as a constant. So if you treat x as a constant, f is now just a function of y, a function of one variable. Integrate with respect to y from y equals C to D. So integrate with respect to y from y equals C to y equals D. So now we just have a function of one variable. We're treating it like a function of one variable and integrating that variable from C to D. The opposite of partial differentiation with respect to y. So we're still treating x as a constant in both cases, but in this case, we're integrating with respect to y instead of differentiating. So if you integrate with respect to y, every time you see y now in the antiderivative, you're going to replace it with C and D, and y is going to be killed off, right? There's no longer going to be any y's left when you integrate with respect to y. They're going to be replaced with numbers. So now you're just going to be left with x's. You're going to be left with just a function of x. And then similarly, we can do the same for an integral with respect to x. So if we integrate x from a to b of a function f of xy, so we integrate that just with respect to x. Now it's the opposite of partial differentiation with respect to x. We're treating y as a constant now. Etc. Integrating with respect to x from x goes to a to x goes to b. Or for x goes from x equals a to x equals b. So I'll call this guy t, whatever. When you do that, when you integrate with respect to x, you're replacing all of your x's with numbers at the end. You're just going to be left with y's. So now you just have a function of y. So we can do partial integration. We can integrate with respect to y, treat x as a constant, integrate as usual with respect to y, or we can do integration with respect to x. Okay, so suppose we have y goes from c to d, x goes from a to b. We're integrating a function f of x, y, like this. So when we write it out like this, we usually will omit the parentheses later, but what we mean is we're doing two integrals here. First, we're doing the inner integral. We're integrating this function of two variables with respect to y first, treating x as a constant, integrating with respect to y from y equals c to d. We're left with a function of x, and we integrate that guy now with respect to x. And when you integrate a function of one variable, you get just a number at the end. This is an iterated integral, right? First, we integrate with respect to one variable, and then we integrate with respect to the other variable. So you do the first guy, you get some function with respect to x. Then you integrate that function with respect to x, and then you get a number at the end. Easiest way to see how to do this is an example. So let's do this really quickly. So suppose we integrate x goes from 2 to 4, y goes from 1 to 9, the function y e to the x dy dx. Let's do this iterated integral. So the way we're going to do this is we're going to look at the inner integral. We're going to do that. And then we're going to plug the result into the outer integral and evaluate that. Okay, so we're integrating y e to the x with respect to y first. So we're treating x as a constant, integrating with respect to y from y equals 1 to 9. So y e to the x. So e to the x is just a constant now. Constant times y, when you integrate, becomes what? Yes, correct. So the constant hangs around, right? And then y becomes 1/2 y squared. So this is 1/2 y squared e to the x is going to be the antiderivative here, or the partial antiderivative. And we're evaluating that from y equals 1 up to 9. So we can pull that e to the x out because it's a constant. It's a common term to everything. And then we get 1/2 times 9 squared. Or sorry, we can pull out the 1/2 e to the x. 9 squared. Then we're just evaluating y squared from y equals 1 to 9. 9 squared is 81 minus 1 squared, which is 1. And so we get 1/2 e to the x times 80, which is 40 e to the x. So when we integrate with respect to y from y equals 1 to 9, we get, we no longer see y at the end, right? Y is replaced with numbers. We're just left with a function of x. We've integrated y out when you integrate with respect to y. And so now we're going to plug that into the outer integral. So the integral x goes from 2 to 4. Of 40 e to the x. Let me actually make this point the right direction. And then that's just a function of one variable. We know how to do that. 40 e to the x, you integrate it. The antiderivative is 40 e to the x. We evaluate that from x equals 2 up to x equals 4. So we get 40 e to the 4 minus e squared. And that's our answer. So far, this has been nothing new. This has literally been doing integrals that you know how to do from 140 and 141, but you're just doing 2 of them. Okay, so we took this guy. First, we integrated with respect to y. Y goes from 1 to 9. Then we integrated with respect to x. X goes from 2 to 4. What if we flip that? And first we integrate with respect to x. X still goes from 2 to 4. And then we integrate with respect to y, where y goes from 1 to 9. Let's see what happens in that case. Do we get the same answer? So I'm going to go through this really quickly. So first we integrate x goes from 2 to 4. Same function, y e to the x. First we're integrating with respect to x. And then we integrate y from 1 to 9. So we flip the order of integration, right? X still goes from 2 to 4, y goes from 1 to 9, but we first do x. So let's look at the center integral. Y e to the x, we're integrating with respect to x, so we're treating y as a constant. So y e to the x is just constant e to the x, that becomes the constant e to the x. So we integrate this, we get y e to the x. X goes from 2 to 4. So that is just y e to the 4 minus e squared. We've integrated with respect to x, we've integrated out x. We're just left with a function of y. And now we integrate that guy. Plug it into the outer integral. So integrate y from 1 to 9 of y e to the 4 minus e squared. With respect to y. So e to the 4 minus e squared is just a constant. Integrate y with respect to y, you get 1/2 y squared. So we get 1/2 y squared times e to the 4 minus e squared. And we're evaluating that from y equals 1 to 9. So we'll pull out the 1/2 e to the 4 minus e squared, because that's a constant. Then I get 9 squared, which is 81, minus 1 squared, which is 1. So we get 1/2 e to the 4 minus e squared times 81 minus 1, which is 80. 1/2 times 80 is 40. Once again, we get 40 e to the 4 minus e squared. Which you notice that's exactly the same as what we got in the previous one. So we switch the order of integration. We get the same bounds for x and y, but this time we integrated with respect to x first and then y. Well, we got the same answer both times. So that's not a coincidence. And in fact, that's how we're going to be evaluating integrals over these rectangles. And so that is the following very important theorem. So important, we name it after a dude. Call it Fubini's theorem. So if you have, this is sort of a technical thing that's going to be true for everything we deal with in this class. But if you have a function which is continuous on a rectangle, x goes from a to b, y goes from c to d, then the way we're going to actually evaluate the double integral of f over the rectangle R is we're going to do either one of these iterated integrals. And in fact, they're both going to give you the same answer. So if you want to evaluate the double integral over R, you do an iterated integral. So you can do x goes from a to b first, then y goes from c to d. Or you can do y first. So the inner integral is y goes from c to d. So you can first integrate with respect to y, and then the outer integral is x goes from a to b. You can do either one of those, and in fact, because they're both equal. So Fubini's theorem says if you're integrating over a rectangle, you can switch the order of integration. You can do x first, x from a to b, then y from c to d, or you can do y from c to d, then x from a to b. Both iterated integrals are going to be equal, and those are going to give you, those are going to be equal to the integral over R, the double integral. And that is the main takeaway from today, how we're going to evaluate these double integrals over rectangles. Okay, any questions about that? First thing, one thing I want to emphasize with these double iterated integrals, make sure if you're writing these out, if we're evaluating these guys, the bounds need to match up, right? So the inner guy, first we're integrating with respect to x. And so the inner integral, the integral from 2 to 4, those are going to give you the bounds of x. And then the outer one is going to give you the bounds for y. And then vice versa. So let me really quickly, we're just going to set up an integral, not actually evaluate it. But just so we can write it down and just so we're clear. Let's find the volume of the solid. Below, the graph of the function f of x, y. I'm not even going to write it out. And above the rectangle R, which is 0, y goes from 0, x goes from 0 to 3, and y goes from 0 to 1. Oh, back. There you go. Okay. Okay, so the volume below the graph of the function f of x, y And above the rectangle R is, of course, the integral over R of the function with respect to area. Oops. So this dA means we say with respect to area. So we know we can do an iterated integral, right? So we can either integrate with respect to x first and then with respect to y, or with respect to y first and with respect to x. So let's integrate with respect to x first, right? So our inner integral, x goes from 0 to 3. So we integrate our function first with respect to x. So our inner integral is going to be dx, and the inner bounds are going to be x goes from 0 to 3. And then the outer integral, dy, and then y goes from 0 to 1. So just make sure the bounds match. If you're integrating with respect to x, make sure the inner guy, if the first integral is with respect to x, make sure the inner bounds are the x bounds and the outer bounds are the y bounds. And then, if you want, you could also integrate first with respect to y. So y goes from 0 to 1, f of xy dy. And then our outer integral is with respect to x, and x goes from 0 to 3. Both of these will give you the same answer. Okay, any questions about that? All right. So that's it for today. So in case you didn't realize, tomorrow is going to be a wellness day, actually. So we're off tomorrow, no lecture tomorrow. In fact, I'm gonna do my office hours on Friday after class instead of tomorrow. So I need to go into Zoom and change those guys. But no lecture or office hours tomorrow. But there is lecture on Friday, normal time, and I'll have office hours right after class on Friday as well, and I'll move a Zoom meeting there. So have a great rest of your day. Enjoy your day off tomorrow, and I will see y'all on Friday. Have a good one, guys.